Let me, you know what this equation's called? This equation is called the Arrhenius equation. Arrhenius equation. There are three forms of the Arrhenius equation that we use. And, let me show you the three forms that we use. We use the Arrhenius equation outright. That is, K is equal to A e to the minus EA over RT. But there's a trick that we often do in Chem, especially with these E functions. You know, if we take the natural log, we can get rid of the E. And that is, if we go ln of K, and then we take the natural log of this, well, the natural log of product is you just add them together. And so doing a little bit of rearrangement, mathematical rearrangement, we get minus EA over R. Minus EA over R is a constant times 1 over T plus ln of A. And so this is this equation here, you know, just with a little bit of rearrangement and using the property of logs. And the thing about this arrangement is this has the y equals mx plus b. And so what we can do is this. This is typically what's done, is you collect a bunch of k's at different temperatures. And so let's plug in temperature here and figure out k's. And so determine the rate constant k at different temperatures. And so we have T1. T1 we get K1. T2 we get K2. T3 we get K3. And then we plot this out. Plot it out. We get an Arrhenius curve like this. You know, the more data we plot out, you know, how much data do we need? Well, that's linear, so technically how many data points do we need to collect?
3.
Well, if you already know it's linear, then we only need 2 points to define a straight line. But the problem is if you only use 2 points to define a straight line, then you're going to be subject to random error. And so then certainty is going to grow. And so the more points we have, the more we can average out the random error. You know, some points are above, some points are below. We average out the random error, and we get a better value. And the value that we're going to get, what are we going to get? We're going to get A from the intercept. Right? So this is ln of A. And so then we can calculate what A is, the frequency factor. And then the slope here is equal to minus EA over R. Well, R is the gas constant. This is where R is equal to thermodynamic gas constant, 0.0820. What is actually what thermodynamic gas constant, or am I doing the regular gas constant here? I was doing the regular. The thermodynamic is 8.3145, right? Joules per mole Kelvin. And so we can figure out what EA is. So we can get the activation energy in A. This plot is called an Arrhenius plot. In the Arrhenius plot, we just plot K versus 1 over T. Arrhenius plot. So we can see an example of Arrhenius plot in our textbook here. Let's take a look at that. Here we go. So this is the Arrhenius plot here. And so how many points do they have? 1, 2, 3, 4, 5, 6. Looks like 6 points. That's pretty good.
Shouldn't it be ln K as you want?
Oh, right. Sorry. This is ln K. Arrhenius plot should be ln of K. You know, for the different ones, ln of K. Thanks. And so we plot ln of K versus 1 over T and get a straight line. From the slope, we can determine what EA is. From the intercept, we have to back extrapolate this. We can get the frequency factor with the Arrhenius plot. Okay, that's Arrhenius plot. Now there's one more thing that we do, and that is this. how many points do we need? We only need 2 points to define a line. Right? Just 2 points to define a line. Arrhenius plot's better. But if we only have 2 points, this is some trick that we do. This is a common trick in Chem. You saw it maybe before in some of the equations that we dealt with. But we do this. Let's say we have 2 data points. We have T and ln of K. And so we have T1, T2. This is going to be, sorry, ln of K1. I should change that over there too. ln of K2. Something like that. So just 2 points. Just 2 points. Well, technically, that's a bare minimum we need. And so we do this trick, which is ln of K2 minus ln of K1. If we do ln of K2 minus ln of K1, then ln of K2 is equal to minus EA over R 1 over T2 plus ln of A minus ln of K1. ln of K1 is minus EA over R T1, 1 over T1. 1 over T1 plus ln of A. So we got ln of A minus ln of A. ln of A cancels out. And so we're left with minus EA over R, 1 over T2, minus a minus, which would give us a plus EA over R, 1 over T1. All right. Now let's leave it at minus, like that. Let's leave it at minus a minus. Petrucci doesn't like that. That's okay. And so what we're going to get is this. We're going to get minus EA over R, 1 over T2 minus 1 over T1. Okay, so well, using the property of logs, when we subtract the 2 logs here, we could divide it what they call the whatever operator, K2 over K1. So ln of K2 over K1 is equal to minus EA over R, 1 over T2 minus 1 over T1. Now, Petrucci doesn't like the negative sign in front of EA. And I was about to get rid of it, but I'd like to keep it. And so if you look at Petrucci's equation, he has plus EA over R, and then he does a 1 over T1 minus 1 over T2. I don't like that, because I always like T2 minus T1, not T1 minus T2, because it just confuses me. And so this is K2 over K1, which makes sense. K2 over K1 is T2 minus T1. And so I'm going to leave the negative sign there. That's the difference. But you know what? I don't care which equation you use. You can use Petrucci's equation or mine. This is Arrhenius with 2 data points. The advantage of this is no need to know A. This is a powerful form because what we can do is we can calculate the rate at any temperature. Can calc rate at any T given any temp given EA. Or we can determine EA or determine EA. So have you ever heard that, let's see, do we have time for this? Oh, is it time?
Yeah.
Okay, I'm gonna stop, sorry.